and welcome to Random Coefficients, Part 2. So today we're going to continue with random coefficients. As I mentioned last week, random coefficients add a level of complexity, but also allow us to model things with a whole bunch more precision. And if I can be quite clear, random coefficients, I think, represent the true superpower of multi-level models, something that you can't do in fixed effects models or generalized estimating equation models. So random coefficients, along with cross-nested models and three-level models, really are unique characteristics of what we traditionally have called multi-level models or mixed models. And that phrase mixed models is something that I'll get a little bit into today. So what are random coefficients? This is review from last week. So random coefficients, random slopes, those are the same thing. They allow us to understand the effect of covariates as they vary between clusters. So our slopes of whatever coefficient that we've been looking at is allowed to vary between clusters. And that's a very powerful tool. Last week I used the example of money and its effect on county spending of public health dollars. We might think adding more dollars to county public health systems would improve outcomes of STD effectiveness or maybe pandemic response, but that effectiveness varies based on how well counties use those dollars. So it's not as if adding $1 is the same across all counties. Adding $1 is going to vary in its effectiveness across different counties based on how effective the counties are at using that money. And that's exactly what random coefficients allow us to understand. We looked at this picture last week to sort of begin to absorb what this is. And again, I know that this is a complicated issue and it adds a level of variability to our models that are already rather complex. But if we look at the top figure here, this is our random intercept model where we have a slope of a line. So this is the effect of elementary school reading scores, for example, on high school grades. And the better students up here are going to be better students here, right? So higher reading scores on the X variable, the elementary school variable, are going to correspond to better grades or better reading scores in high school. That's not surprising. And we also know that different schools have different levels of effectiveness, and that's represented here by different intercepts. So our zeta 1j, we're going to add a 2 zeta, right, as you know. Our zeta 1j represents the difference in intercept. But the key to note about the random intercept model is that these lines are parallel. We have not allowed the effect of reading to vary between schools. We've just allowed the intercept of the high school school. You know, some schools have worse students, some schools have better students, and that's represented by the intercept. But it may be that schools perform differently in taking students at a certain level and moving them to a different level. We call that learning, right? So different schools may do a better job at teaching students, and those differences would be reflected in differences in the relationship between elementary school reading scores and high school reading scores. And we saw that down here, where we not only have two parallel lines represented by a shift in intercept, but we also allow these lines to vary across in terms of the relationship between the X variable and the Y variable, which we otherwise would call the slope. So the slope of these lines are allowed to vary across schools. Different schools are going to have different levels of effectiveness in transmitting, taking students with a certain high school or a certain elementary school reading score and transmitting that into high school scores. And we can see that in the formula here, where we have our intercept represented by our grand mean, our traditional intercept, and the school-specific variation, which we call a random intercept. So that's a random intercept. And here's the slope for the effectiveness for the relation that expresses the relationship between elementary school reading scores and high school reading scores, and we allow that relationship to vary across schools. So we allow the starting point for schools to vary. Different schools have different levels of students, and we allow those schools to differ in their effectiveness in teaching, and that's represented by this zeta 2j. So that's a review of last week. We also discussed different model assumptions, and there's a lot here, but I just want to focus on this thing down here, which we're going to be spending more time in later today, that we do allow the zetas the zeta 1, 2, and we could have 3, 4, 5 zetas, right? We can add as many random coefficients as we want, although they're really costly. Those are all correlated within cluster. So we're going to get a within cluster correlation, and that represents the relationship between where in the context of the analysis that we're talking about here, where a school starts and how effective it is at transmitting information. And so we can model that directly using a covariance matrix. And we talked about that a little bit last week. We're going to continue with that this week. This is a picture of the covariance matrix. So here is the variance of our zeta 1. So that's the variance of our random intercept. Here's the variance of our zeta 2. That's the variance of our random coefficient. And then this element right here represents the covariation between 1 and 2, zeta 1 and zeta 2. And you will note that this is the same covariance. A covariance of 2 with 1 is the same as the covariance of 1 with 2. So that's represented here. So we have a covariance matrix. There's lots of ways that there's a couple ways that we can deal with it. One is to assume that these numbers here are 0, that this term is actually 0. One way is to directly model it. And the directly modeling it way is the way that we're going to prefer in this class. I will note that as you add more random coefficients, you get more covariances. And those are, again, costly things to estimate. And so one should be cautious in how many random coefficients you put in the model. You really need to be able to support it. Although often you want to have many. Like I said before, I've had models that have had 70 or so random coefficients, and those models took days and days and days and days and days to run. So let's build up to our model again, and in the course of doing so, I'm going to show you a new way of thinking about these models. That is a way that's common in education research and is most and is expressed also in M+. If you model these. If you do multi-level modeling in M+, you're going to have to express your models in this way. So I want you to be familiar with it, but I also want you to be able to think in these terms. I think that there's a real value, as I've mentioned before, in understanding these linear formulas. They really help us think through what is possible with models, and once you become fluent in these kinds of models, not only will you have access to more literature, but you will also be able to think through your models in a more concrete term, because you can write this stuff down. And you can think about your models in these terms. So this is a language. It's hard to learn, but once learned, it opens up doors for you. So I want to spend a little bit of time going through this alternative formulation. So this is the basic random intercept model that we've worked with. Here's the random intercept. You can see the random intercept estimated here. Again, we don't see the zetas in this model. We call this psi. And that's represented here with this variance term. We have the overall intercept, so that's the grand mean. This represents the variation around this in terms of schools. And so some schools have higher levels of effectiveness, some schools have lower levels of effectiveness. Here is the average across all schools for how reading is transmitted from elementary school to high school. So so again, these are standardized, and they're standardized at mean 0 with each 10 units represents a standard deviation. So this is about a 56%. So each unit increase in reading scores is associated with a 56% increase in high school graduation. So that's a pretty substantial transmission of elementary school reading scores to high school. But it may be true that some schools do a better job of teaching students, and so take students and move them up at a steeper slope. Some probably just take students and they just stay where they are. They don't really they don't take poor performing students and make them better, or take excellent students and make them even better, right? So that's the idea of the slope of LRT, which is our reading schools. So we can allow these schools to have different levels of effectiveness, and we do that by adding this random coefficient term here. So this random coefficient term represented here is it represents the variation around this slope. So this is the variance around this slope for schools. So some schools do a better job of this, some schools do a worse job of this, and we have now captured that in terms of variability. All right. So let's take a look at the two-stage formulation. So what we have done is added a random intercept and a random slope, and this is all consistent with what we did last week. We have them as two separate terms. We have them as the grand intercept and the variation around that intercept. So this right here is beta 1, and this right here is the variance around beta 1. This is beta 2, and this is the variance around beta 2, right? But the zetas are the things in themselves, right? So the zetas actually represent the deviation between these means. So we can represent this as one term, beta 1j, right? So it's our first term, which we call our intercept, and it represents the composite of these two. We can also do the same thing with the slope. So we have beta 2j. So each school has its own slope, and each school has its own intercept, right? We had characterized the deviations with these zetas, but now we're just adding these together because you know how to add, right? And so we can just combine that in one term. So now we have one formula down here where we have yij as a function of beta 1j plus beta 2j times beta xij plus our error term over here. So what we've done is we've split these guys, our beta, we've combined our beta 1 and beta 2 into these composite terms, and so we can think of them this way. This is called the level 1 model. These are called the level 2 models. And when you do Raudenbach and Bright, I'm forgetting how to pronounce his name now, represent one of the earliest formulations called HLM, hierarchical linear model. They had a program called HLM2, and they formulated it in this two-stage model. As I mentioned before, M+ uses this two-stage model, so you have to specify a level 2 model and a level 1 model. And what this separation of these models will do is allow us to think through some more complicated issues in ways that I think make more sense. Now, again, this is going to be a little bit challenging, but I think if you spend some time with this and master this, this really becomes a tool in your toolbox to think through complicated modeling issues. It also opens doors to a literature that specifies these models in this formulation, and some of you might go on to use M+, and it would also allow you to use M+ as well. And then, just in general, thinking flexibly about these models is an important thing as well. So this formulation here is no different. This is the same model that we have run the entire time. And you can see that here in this picture, where this is the model that we had before, where we had our intercept and our coefficient, and then our random intercept, our random coefficient, and our error term. You'll note here, and some of you have asked about this, when we refer to these models, and sometimes these models are referred to mixed, fixed, and random effects models, the term fixed here gets confusing because we've talked about fixed effects models, and this is a little different than fixed effects models. Although it's the same thing, but it adds confusion because we talked about a specific specification of fixed effect. What fixed effect is a thing in itself, the coefficients that you've usually interpreted. In the context of this is our intercept, just our regular old intercept, and this is our regular old coefficient, and those are considered the fixed portion of the model. Our random intercept, our random coefficient, and our error term, those are considered the random part of the model. And again, I will note that we always have had this. This is our fixed part. This is our random part. And all we've done here is the only difference between these two is I just added this gamma and mu instead of zeta and beta, just to keep these. This is the two-stage formulation, and this is the reduced form formulation that we've been dealing with the whole time. But now I'm going to do is show you how to use these level 2 models to think through multi-level modeling, and particularly with random coefficients, which can get confusing. And I think that the other thing that this helps us understand is the separation of variables into two different groups: variables that vary within cluster, or the within variables, and variables that only vary between clusters. And the within cluster variables, in this case, the reading scores, right? So we've been using the LRT variable as reading scores. Those vary across students. Different students have different reading scores. Now, we think they're nested in schools, but they're also, but we have individual student scores. So that's a level 1 variable. But if we were to put in a level 2 variable, for example, the type of school, whether it's a mixed school, a girls' school, or a boys' school, that's a level 2 variable. And by separating the level 1 and level 2 models, we can begin to think about that. So here is our level 2 model for the random intercept, right? So this is our random intercept term that represents the composite of our intercept, our constant. That's this guy right here. It's the same fellow we've always been working with. And we have our random intercept over here, and while we don't see that term, we do see the variance of that term, and that is represented with this fellow right there. And what we've added here is a variable that represents the different types of schools. The baseline here is mixed boys and girls school, and then we have a coefficient for boys school and a coefficient for girls school. And so the constant here, because remember, 0 is the mean of LRT, it's centered. This represents the average score of the average reading score of a mixed school. Boys schools get a little bit of a bump in terms of reading scores, and girls school get an even bigger bump in terms of reading scores. You'll note that the boys school is not statistically significantly different from the mixed schools, but the girls school is statistically significantly different from the mixed school. Here we have our random coefficient. So this represents the variation around this term here, and that's represented by this term here. So this term is the variance of this. This is, as we mentioned before, is the variance of that. And then this represents the correlation between the random slope and the random intercept. We're going to spend a little time later in this lecture talking about how to interpret that and breaking that down in a similar data set. But for now, suffice it to say that there is a direct positive relationship between reading scores and high school scores in terms of the above and below the mean of the intercept and the mean for both the intercept and the coefficient. And again, that's a complicated issue. I have a little strategy that I use that I got from the multi-level modeling in plain language book. It's explained really well there, but we're going to go through that later. But suffice it to say here, what we have is a model that has the constant term. We have a term for boys' schools. We have a term for girls' schools. We have a coefficient for reading scores, and then we have this random component. And this is our reduced form model, but this is the level 2 model where you'll note these guys don't vary within school, so there's no I there, right? There's a 1 representing boys and a 2 representing girls, and then this ends up being the coefficient for the mixed schools, because that's what happens when you have this is 0, this is 0, then this ends up being the mixed school. But the level 2 formulation allows us to separate out things that are going on at level 2 from things that are going on at level 1. So this is a level 1 variable. These are level 2 variables. A little bit unnecessary when we're just talking about the intercepts. But when we start using the slopes, random slopes as well, then it gets a little bit more helpful, I think, for us to think about it in terms of this two-stage formulation. So here is a level 2 model where we are looking at the effect of boys and girls schools on the slope of reading scores. What you will note when you add this in, right? So this is the part, this is our beta 1, J, right, which we saw from that very simple formulation in the beginning. This is our beta 2J, right? So we started off with a coefficient and then a deviation from that coefficient, right? So this is our random coefficient here. And we've added these terms, which are the boys' school and girls' school terms. And you'll note when you multiply this out, what you get is 2 interaction terms. So this is what is called a cross-level interaction. You have a level 2 variable interacted with a level 1 variable. This is reading scores. This is boys and girls schools. So now the question becomes, we have a slope. That slope has an average slope. It has a deviation from that average slope for boys' schools. It has a deviation from that average slope for girls' schools. And then each school itself is allowed to have variation. So some schools, regardless of whether they're boys' schools or mixed, right? So this ends up being the mixed coefficient, the boys, this is the boys' coefficient, this is the girls' coefficient, and then this is the school effect, right? So each school can vary, and what these schools are varying around is the girl intercept, the boy intercept, and the mixed intercept. So we have 3 different slopes and then variation around that slope. And by thinking of it in terms of this level 2 variable, I think it makes it a little bit more clear what's going on, because this formula down here gets a little bit complicated. And so for me, thinking about it this way gives me an opportunity to think through things in a little bit more of a complex manner. It breaks down the complexity into different chunks that I think are more meaningful and understandable. And then we can directly estimate that model. And the model is estimated as a interaction model where we have interacted the school type with the reading score. What we find here is that there's not a statistically significant interaction. There's no evidence of that interaction. And so in the end, I would not include this as a point of fact. It didn't add much. But on the other hand, what I think we were able to do is think through this issue. And one of the things that we're going to do as we move forward in this class is we're going to develop more and more complex models, and this 2-stage formulation is going to allow us to think about that. As you can imagine, once we get to 3-level models or 4-level models, right, you're going to want to split up these different models at the different level to understand what it is that's going on. It's one of the tools in the toolbox we have for properly estimating and thinking through our models and understanding our models, as I've been highlighting as we go through this class. We really want to understand what our models are saying. We don't want to just press buttons. Alrighty, so that is the 2-stage formulation, and what I want to do now is go back to a quick detour to think through some of the tools that Stata has to think about these in terms of SEM models. We looked at SEM models for longitudinal data, and in those longitudinal models, you'll recall that for each wave, so if we have a data with 4 waves, we had an equation for each of those 4 waves, and then we fixed those coefficients across the waves to be the same, and that's how we estimated a multi-level model using using an SEM framework. But that doesn't work in the context of a school. We would have to have each student would have to have their own equation, and that just doesn't work. And so what in some of these programs, and I don't know about SAS. I don't think SAS has this capability, but I do think Lavaan in R has this capability, which is to do multi-level models of using an SEM framework. So here we have that same model that you just saw without the interaction. because we don't need the interaction, as we learned. And what we have here is the random intercept, the random slope. This is our residual term, so this is our epsilon ij. And the random intercept and the random slope here are latent variables. You'll recall what a latent variable is. We have a fixed mean here of 0, and we often fix the mean of our latent variables, right? So we have a fixed mean of 0. And then there's some distribution, and we almost always assume that our latent variables are normally distributed. And then we estimate a variance parameter for these latent variables. You will note that that is exactly what a random coefficient is. There's no difference between what a random coefficient is and what a random and what a latent variable is. They're two sides of the same coin. When we get to growth curve models, we'll really begin to see some of the benefits of doing this. So once we get models that allow us to take something like a slope, we can then begin to regress on this slope, and that's a really powerful tool. Because we might want to understand what leads to some schools being more effective than other schools, right? And then you can actually build in that regression using the SEM capabilities to get some answers to those kinds of questions. But in Stata, we can formulate it like this. There's also another way we can formulate it in Stata, which is using the SEM command. And I'll just show you right here. So this is the builder version. Oops, I forgot to decrease. I forgot to get rid of the estimates. So we'll clear those estimates and we will run those estimates. Because I did not do that. Now we can run those estimates. I will note that using this formulation in Stata requires the GSEM command, and the GSEM command does not allow us to use FEML. So this is a deviation from the other rule that when we talked about the longitudinal data, we were able to use FEML. But currently in Stata, we're not allowed to use FEML in this formulation. So we'll talk about that more in class. But I will note these are the exact same findings that we got from the other model. It's exactly the same model. You'll note that we allowed the correlation between the random intercept and the random slope to happen. That's this term right here. So we directly modeled that correlation. So you can do all of the same and reproduce the exact same model. So here's our coefficient for LRT. Here's our boys and our girls school. You'll note that the boys school is not statistically significantly different from the mixed schools, but the girls school is. This is the variance of the random intercept. This is the variance of the random slope. If you see a difference between this and the other one, you'll note that in the other one I use standard deviation, not variance, and so that represents the difference. If you convert these to standard deviations, you'll see that this is exactly the same, and then these are the same as well. So we were able to replicate the model using an SEM version. I think that just seeing that and recognizing that Stata has this capability, as well as some of the other programs like Lavande, gives us an opportunity to think through some of the models that we're going to have subsequently in a much better way. So moving on to the next topic, which is interpreting correlations or those random effect covariances. We had talked about this a little last week, and I didn't think that I did a particularly good job of explaining this. So I wanted to take a little bit of a closer look at how we can understand the correlation between the random intercept and random coefficient. And I think, as I've mentioned many times before, when faced with complexity, often the simplest thing to do is just graph it and look at things in a concrete kind of way. I'm a very concrete thinker as opposed to an abstract thinker. And so this really helps me think through things in a way that allows me to explain it to other people. I would also highly recommend this for any interaction terms. That's why I'm such a big fan of things like margins or proc PLM and SAS. The opportunity to really think through things in concrete ways is how I end up understanding what's going on with my models. And so here we're going to try and understand what that correlation is between our random intercept and our random coefficient. So first of all, you need to use the covariance unstructured term in order to get the right estimates. I think the baseline in Stata is to not have a correlation estimated, which is assuming that the correlation is zero. It's not that there is no correlation. It's not the absence of correlation. It is that the correlation is fixed to zero. And that's a very specific model. So I often add this additional this additional option of covariance unstructured, which then directly estimates the correlation between the random intercept and the random coefficient. And I will note that if you have multiple random coefficients, you're going to have multiple correlations, right? So you're going to have things correlated with each of the things correlated with each other. So it increases quite rapidly as you increase the number of random coefficients. You increase the number of parameters you have to estimate quite a bit. And you will find when you run these models using your own data, if you start running more than one random coefficient at a time, that you end up getting a very, very slow draw on the model, as well as difficulty with model fit. Sometimes models will just implode if you put too many coefficients in there, random coefficients. There's a lot of reasons for that, which I'm happy to talk about on an ad hoc basis with you guys as this problem comes up. So one thing that it's important to do, and I mentioned this last week, but I just want to reiterate this, is it's important to center your variables. And here we're not talking about the group mean centering that we've used before to separate the between and within, but rather the overall centering, the centering to the grand mean. And the reason is, as we discussed last week, that the variance of the model, the total variability of the model, varies across our x variable when we run a random coefficient on that x variable. And you can see why with this picture here. So this is the formula down here for the total variability. And anytime you see a multiplicative term, you know that there's going to be trouble. This multiplicative term suggests that the size of this term, right? So this term plus this term is what we were dealing with before. The variance here is psi, the variance here is theta. That's how we got our interclass correlations and our R squared and all of that stuff. There's nothing multiplied here, right? These things are things in themselves. But this term varies across the x. And so and where this term gets when we look at our models in Stata, right? So here we have the variance component. No, let me use a traditional one. Here we have the variance component for our random intercept, our random coefficient. This is estimated at 0, where LRT is at 0. Now LRT is meaned at 0, right? So it's a z-score with each 10 units representing a standard deviation, but the mean of it is 0. So it's at the right place. It's at the average, which is a good place to start. You might have other places where you want to center it. There might be other meaningful places, but you can see why the variance varies on x when we allow for different slopes, because the variability of the model here is different from the variability of the model here is different from the variability of the model here. And because it estimates it at 0, we want to make sure 0 is a meaningful term. And that's why we center at 0. So we've used centering for a lot of different things. We've used centering to understand intercepts. We've used centering at the group mean to understand deviation from the differences between the between and within. And here we're using centering to place the variance measure at a place that we find meaningful. If there's no data over here, then it's a little unclear what this variance parameter means. We want to have it at a place where we have data and where it's actually meaningful. So that's why we center. So looking at some data from the multi-level modeling and plain language books, this is chapter 3 out of there. we're again using education, and we use schools in this context because schools represent really the different, there's a few kinds of things, types of data that we model. The longitudinal data, which we've covered in the past. I really try to focus on these other forms of multi-level models, because we're going to get a lot of longitudinal in the coming weeks, specifically starting next week. So here we have a variable called ESCS, and what that represents is the family's capital. It's a composite variable of education, employment, and assets, and I've centered it at 0. So this is just me. I'm sorry, I mean centered it, right? So the 0 on this variable is the mean family social capital. And here we have reading scores, and you see the Z here, so it's Z transformed. So again, that's also centered at 0. So 0 represents the average reading score. So family capital is strongly associated with reading scores. That's not surprising. A lot of what this assets, things like you have books in the house and things like that, and then parents' education and employment status and other things like that. So we have the intercept, we have the slope, we have the variation around the slope and the variation around the intercept, and then we have the correlation between the intercept and slope. And this is what I want to focus on here. What does this -3.9 mean? Again, this is not the easiest thing in the world to understand, because we've abstracted now. We're not thinking of data points in particular. We're thinking of intercepts and slopes. How do the intercepts and the slopes vary? So let me walk you through what I'm going to do here, and then we'll take a look at a picture. So I'm just going to grab the data, and then I'm going to do the centering and label the variable so I can remember what it is. And we'll take a little bit of a histogram look at what the data looks like. And you can see that the data, family capital, it's centered at 0. There's some lower tail here, but nothing surprising about that variable. And then we're going to run our random intercepts model. And this is just our basic random intercept model, estimating the effect of family capital on reading. There is variation, clearly. There's variability around schools' reading scores. That's not surprising. We already know that. Here we're going to run our random intercept model, and you'll note that I did store RI. That's our random intercept model. And now I'm going to do, when I run my random coefficients model with this ESCS variable in it, I'm going to store this as random coefficients, and then I'm going to do the likelihood ratio test to see if the random coefficients model improves on the random intercept model. And when we do all of that, what we see is that the random coefficients model does improve on it, and you can see that in this standard deviation, which is clearly not 0. The confidence interval is well away from 0. So we have a pretty good idea that there is variability in schools on how much the parents' family or the family capital affects reading scores. There's a positive relationship between family capital and reading scores, but some places have a less strong relationship between family capital and reading scores. Some places have a more strong relationship of family capital and reading scores, and that's this term, right? That's the variability around this. That's our random coefficient. And then the variability around our random intercept suggests that this varies, right? So different schools have different reading scores on average, and different schools have different effects of family capital on those reading scores. And it turns out that there is a negative relationship between that variability for where the schools are in terms of their average reading scores and how effective they are at transmitting, well, let me take a step back and say how much family capital predicts reading scores. So what we can do is we can grab the random intercepts. We've been talking about them in terms of variance components, but we can also get the zetas themselves. And here we do predict U1 and U0. And these, we've been calling them zetas. So let me just call these zetas. Right. So I'm just going to get zeta, our random intercept and our random coefficient. I get that by doing in Stata, I do that predict these are the names I made up, right? You just saw me change them. And then this is the random effect. This is asking for the random effects. I could also ask for the linear combinations, which you could do as well. But here we're just going to look at these deviance components, which represent the difference. So this Z1 is going to be each school's difference from this term. Our zeta, zeta naught is going to be the difference between each school and the intercept. So this represents the random coefficient. This is the random intercept. I run this. Stata calculates this. You can actually see the term itself. So this is this school's. So this school has a little bit under the average effectiveness. Under this school is a little bit above the effectiveness. This school is a little bit this school has a steeper slope than the average school in terms of the effect of family capital on reading scores. So this is a school right here, and I know so centered at 0, right? So all of these random intercepts are always centered at 0, but here we have a school that has a steeper slope. That means that I know more about a student's reading score if I know what their family capital is. Whereas a school with a negative score, here it's almost exactly the opposite of that other school. This school, I know less about a student's reading score if I know what the family capital is, right? So family capital has a less strong relationship to reading in this school, and family capital has a more strong relationship to reading in this school. Here's my random intercept. This school has above average reading scores. The school has below average reading scores. Again, the average is going to be 0. And so I know this school is below the average. This school is above the average. So because these are the same across all schools, I just want to pick one of these because I'm interested in the school levels. And then we're going to run a scatter plot to look at the relationship between these two variables, these two coefficients here. And here you see the scatter plot. If we can go on over back to PowerPoint, I will show you some text that I've added to this. So what I've done here is I've broken it into quadrants. And again, 0 is the mean for these. So schools so the x-axis is the random intercept. The y-axis is the random slope. So schools on this side of the line, they have a higher than average reading score. Schools on this side of the line have a lower than average reading score. Schools in this above this horizontal line, they have a steeper than average slope for the relationship between family capital and reading scores. Schools below this line have a lower than average slope for the relationship between average reading scores and family capital. So if we just take a look at, so the negative correlation is because the data moves along this line, right? So if we were to run a regression of these things, you would see that the slope was negative here. What in this quadrant, let's call this Q1. What we have here is lower than average school reading scores, right? Because they're on this side of the line, this side of this line, but higher than average effect of family capital on reading scores. So we have it here. So these are schools that have students that are below average on reading, on average, and the effect of family capital is more important in these schools than it is in schools that are below this line. Whereas this quadrant, and let's call this Q2, these schools have higher reading scores on average, but the effect of family capital is lower. So it turns out it's a little unclear what that means in practice, right? I don't know enough about schools or research on schools to fully understand what that means. But by breaking it into quadrants, what we're able to do is think in very concrete terms about above and below average average intercept and average slope, and begin to pull this apart. Now, again, I am now completely out of my depth in terms of understanding what this means, but let me just venture a guess. Down here, you have schools that have higher than average reading scores. So these are schools in relatively wealthy districts. I'm going to guess those schools have more money, and that money allows them to overcome the effects of low family capital. So for example, one of the things that's measured in family capital is, does the student have books? Does the student have a computer at home? If you live in a richer district, there are fewer students that need those things and more money to add those things. So you can give books away to students. You can give computers away to students to ameliorate the differences between families in terms of their education. It also might mean, it could mean a lot of other things, right? It could also mean that families move into these districts, poor families move into these districts and sacrifice, and as such, they value education more. So there's a lot of ways that one could interpret this. And again, I want to be cautious in interpreting that. But if this were your content area, I think it behooves you to really think through what correlations between the intercept and the slope truly mean. And it can help you pull apart your data. And get a better understanding of how your model is functioning. Does that seem like a reasonable thing? Or is that something that's not making much sense and you need to go back and think through your model a little bit more? So another tool in the toolbox, we've gotten 2 of them today. We've added our 2-level model formulation. We took another look at SEM and we began to pull apart some of these correlations between our random intercepts and our random coefficients. I look forward to meeting with you in class and talking about this in more detail. Until then, take care.